The F1 season has only just begun off the back of the preseason shakedown in Barcelona. We've got new cars running, Aston Martin barely made it to the track, and Williams didn't even make it to Barcelona. But look at the car they did reveal though. Go Williams indeed. But even before any car had begun running in Spain, we were hit by our first controversy of this new era of Formula One. Mercedes and Red Bull engines might be illegal. My name's Barrion, and I'll be analysing the situation using my knowledge and publicly available details to help you come to a decision on which side to take in this controversy. If you find this video interesting, hit the like button and subscribe, as I intend to do more Formula 1 videos in the future. Now let's start from the beginning back in December, where Ferrari were doing some research via information gathering, simulations and technical analysis. All normal activities involved in finding an estimation of where your team's car stood before the season formally begins. However, to their surprise, they discovered that their powertrains were potentially operating about 15 horsepower less than that of the Mercedes and Red Bull powertrains. But that couldn't be right, could it? Not when the new rules and regulations are supposed to try to create closer running between teams, as they enforced a 50-50 hybrid split between renewable fuel and electric power. And in the world of Formula 1, 15 horsepower is a lot, because it could potentially mean a deficit of about 0.4 of a second, which is the difference between being in pole position or 9th place in last year's qualifying for the Hungarian Grand Prix. So what did Ferrari do? They began further investigations into what could cause such a significant difference. And the answer they came to was Mercedes and Red Bull were likely to be operating at higher compression ratios than what were permitted by the regulations. Somewhere around 180, which was last year's maximum compared to this year's maximum of 116. And so Ferrari did what they usually do in these situations. They filed complaints to the FIA, claiming these as rule violations, and therefore accusing Mercedes and Red Bull powertrains of cheating. Of course, both Mercedes and Red Bull are choosing to deny these allegations, and instead calling this a result of a loophole. Fast forward a little bit, and Ferrari are now joined by the other powertrain manufacturers of Honda and Audi, completing the split between 6 teams on the grid that have this potential 0.4 advantage, and the other 5 that do not. We'll get into the nitty gritty of the exact rule or regulation each side is using to argue their case later. But first, there's probably something you're wondering. If the regulations state that the maximum compression ratio must be 116, how is it possible for the Mercedes and Red Bull engines to have a compression ratio around about 180? Well, if you've been fully immersed in this controversy, you will probably have your answer, which is thermal expansion. If you've taken high school classes in physics, you might remember that when any state of matter is heated, it expands due to the atoms becoming energized. Whether the object is a solid, liquid, or gas, thermal expansion will occur to some extent. All of these types actually happen in Formula 1. Fuel is ignited, car parts get hot, and when the air conditions get hot, either through exhaust fumes or the weather, you can all see thermal expansion occurring in some way. But to know exactly how this affects the compression ratio, we first need to understand the stages of the engine and how the compression ratio is obtained. Here is an internal view of one of these engine cylinders. Unlike most modern road cars, F1's V6 engines operate using the more efficient 4-stroke process compared to the 2-stroke one, so we'll just focus on that. First, the piston moves down, while a camshaft rotates to open the inlet valve, letting the air-fuel mix into the cylinder. Air is mixed with fuel to make it combust more rapidly, since we want the fuel in the cylinder to be used completely for that one engine revolution. The piston then moves up, compressing the air-fuel mix, and we can see the intake valve is now closed. The compression of the fuel here makes it pressurized, storing the energy taken to compress it, along with the energy it already possesses as internal potential energy. So when the fuel is then ignited by the spark plug operated by the ECU, the energy is released explosively as kinetic energy, forcing the piston down and warming up the surrounding area with thermal energy. The movement of the piston here causes the crankshaft to rotate, and this is what gives power to move the wheels of the car. As the piston reaches the bottom of its movement, the exhaust valve has now been opened, so when the piston moves up again, it forces out all the gases from the fully ignited fuel out of the engine. The piston, still influenced by the ignited fuel, then moves down and the process starts all over again. The faster the system moves, the higher the power produced, and the car accelerates and moves faster. Now, I know what you're thinking. Baryon, you've mentioned compression, but where is the compression ratio? It's quite simple, really. If you've been paying attention, you might have noticed there's a small section in which the piston cannot reach within the cylinder. And in this lies the key to what the compression ratio is. If we look at the equation of the compression ratio and what each variable visually represents, we can see it is simply the max volume of the cylinder above the piston, where it's at the bottom dead center, over the volume of the section above the piston at the peak of its movement, at its top dead center. Now imagine a spring. Compress it a bit and it won't spring up too far. Then compress the same spring more and it will travel further. More compression equals more energy released, and this is the same case for the fuel in the cylinder, in which we can relate the compression ratio as such with the length of the spring at the start with the length of the spring of when it's compressed. Now what about thermal expansion? Well, we already know fuel is ignited and therefore will heat up the surrounding area. It's actually something that all engineers must take into account when designing an engine. Because of thermal expansion, engineers cannot assemble a fully tight fit between the cylinder and the piston, something that is required to prevent some leakage of the fuel, ensure the system is fully efficient in creating horsepower, as well as ensuring proper thermal dissipation through the engine walls for cooling. So instead, the piston is built so that once the engine starts running up in temperature, the thermal expansion caused by the ignited fuel will seal the cylinder. But we cannot allow too much thermal expansion or the piston will rub against the cylinder walls and increase engine wear. So to control this, the piston and cylinder will be made of different materials. The cylinder typically of cast iron or steel, and the piston are of an aluminium alloy, usually which expands about 2 times that of iron or steel. There are different aluminium alloys though, each with differing amounts of thermal expansion, so depending on what you choose, you can control the thermal expansion to a certain degree. As mentioned before, the thermal expansion will also affect the compression ratio. If we think about the piston expanding more than the cylinder, it stands to reason that the volume that the piston can push through has also changed. With the piston head expanding, the volume left at the top is now smaller, though this is only by a small amount since the cylinder head will expand more through its diameter than its length. The effect is however further magnified if we take into account that the connecting piston rod, through thermal conduction with the heating piston, will have its length expanded too. With the piston arm longer, the piston can push through the cylinder, and yet the volume when the piston is drawn back is kept roughly the same since the piston head's length expansion is minimal. Putting all these changes together, we can see that the compression ratio will increase somewhat, something inevitable for all engines. If we manipulate the materials, we can make the thermal expansion work in our favour to increase the compression ratio. One of the likely things Mercedes and Red Bull have done. There must be some design choice made to create such a change from 116 to 118 in the compression ratio, but all we can do is speculate. For instance, maybe there's a section at the top of the cylinder that thermally expands more than the rest of the cylinder to reduce the volume remaining during compression. It's a simple solution and probably pretty crude though, so it's likely not what is being used, but it's just one idea of how thermal expansion might be utilised. So now we understand the engineering behind the incident of what the compression ratio is and the effects of thermal expansion. But if it's something inevitable, why are Ferrari, Audi and Honda still arguing their case? Well, it's all about the wording in the rulebook, specifically section C of the technical regulations. And within it lies the loophole and also why the other teams can argue a case against it. Firstly, let's look at Article 5.4.3. It reads, no cylinder of the engine may have a geometric compression ratio higher than 16, and that the procedure to measure this value will be detailed by each PU, that's power unit, manufacturer according to the guidance document FIA F1 Doc C042, and executed at ambient temperature. At ambient temperature? Yes, this means that the compression ratio reading given to the FIA is taken when the car is not hot. and not when the compression ratio has been increased through thermal expansion. And since there's no check anywhere after this cold reading, it's possible to get away with maxing out the compression ratio for the cold test and reaping the rewards of an increased compression ratio through this thermal expansion. Hence this being a legitimate loophole, and the FIA shooting themselves in the foot with the hope of close engine running. The only issue with this lies in Article 1.5 though, about compliance within the regulations. Formula 1 cars must comply with these regulations in their entirety at all times during a competition. So if an F1 car is measured to have a compression ratio of 1/16 or less, but then while running the compression ratio is greater than this maximum, they are breaking this regulation. And this is why Ferrari, Audi and Honda have a legitimate case to argue. But now we have a bit of a problem. Mercedes and Red Bull can circumvent the maximum compression ratio, yet the rules allow this to be unchecked by the FIA, despite the compliance rule being broken? Oh, good job, FIA. You just played yourselves. Maybe think of the checks you will use before implementing them next time. So, what does this mean for the engines going forward? Well, up until now, the FIA gave the Mercedes and Red Bull engines the green light. But recently, it came out that the FIA put into work a hot test for the compression ratio, with 4 out of 5 manufacturers needed for the new regulation to go ahead. This is something that is likely to happen and not happen, since Red Bull are actually on the fence for this argument, maybe having a safer engine compression ratio powertrain, as well as explore the realms of the loophole. Though it has also come out that Red Bull have not been able to replicate Mercedes in utilising the loophole, and were actually the ones who informed the other teams of the existence of it and what Mercedes were doing, therefore throwing Mercedes under a stampede of pressure from the other teams. At the moment though, we are getting mixed information of whether it will be enforced this season or the next. I am more of the opinion that if there is a regulation change, it will happen next year, much like how most past loopholes were resolved, like McLaren's 2017 F-Ducts, Braun's double diffuser, which actually was allowed for 2 seasons before the loophole was resolved, or even Ferrari's fuel flow solution from 2019. Maybe it will be seen as against the spirit of the sport, and Mercedes will be fine like Ferrari was in that year. But what are your opinions on this whole situation? Comment down below with your opinions and feel free to ask for topics you'd like me to talk about. Maybe I'll choose as my next video, who knows. If you like this video, give it a thumbs up and hit the subscribe button for more Formula 1 information. And thanks for watching. I'll see you all in my next video.